Newton's second law of motion. We talked about the first, which talks about when all the forces add up to be equal to 0. Now we're going to see what happens when all the forces, the net force, does not add up to be 0. And this allows us to relate force and mass to acceleration. Okay? So previously, when we talked about linear motion, we didn't talk about why things move. We just talked about how things move. Now we're going to say things move a certain way because of force. They accelerate the way that they do due to a net force acting on the object. Now Newton's second law, again, is very easy to remember. I always try to remember it by just thinking FAMA. F equals ma. Force equals mass times acceleration. It's important to note that this is not just any old force. This is the total force acting on the object. Mass is the amount of inertia that the object has, and obviously the acceleration is the rate at which the velocity changes. So F equals ma, very, very important equation to remember because it basically tells us why things move the way they do. So consider an 80 kilogram person. Let's say that they accelerate at a rate of 2 meters per second squared. What would the net force have to be on that person, probably from their legs, or probably on a bike, in order to accelerate at that sort of rate? Remember, every second that goes by, they're going 2 meters per second faster. Very simple. As we said, the net force, the total force acting on the person, is equal to their mass times their acceleration. 80 times 2 is 160. Kilograms, meters per second squared, have units of newtons. Newtons are the SI unit for force, named after Sir Isaac Newton. Okay? What if we want to calculate acceleration from the force and the mass? We just saw calculating the net force from mass and acceleration. We can take the same equation and just turn it around. Acceleration is the total force divided by the mass. Makes sense. The more force something has on it, the greater it's going to accelerate. The less mass it has, the greater the acceleration for a given amount of force. So, by Newton's second law, the larger the force, the greater the acceleration. The greater the mass, however, the lower the acceleration. Remember, mass is a measure of inertia, and inertia is the resistance to change. The more mass something has, the more it's going to resist a change in velocity. Acceleration is change in velocity divided by time. The more it's going to resist that, and the lower the acceleration is going to be for more mass. So if you want to maximize the acceleration for any system, okay, the force must increase while the mass must be kept at a minimum. Again, let's use the same equation, F equals ma, but we'll solve for a instead. F equals ma. Divide both sides by m. That gets rid of the mass on the right-hand side. Move the a to the left-hand side, and we can solve for a. Consider a 1,500 kilogram car. It's pretty typical for a sedan. Exerting a force of 2,000 newtons, basically from the engine putting torque on the drive shaft and the drive shaft putting force on the tires. How fast does it accelerate? Very simple. Acceleration is proportional to the net force divided by the total mass. So 2,000 divided by 150 gives us an acceleration of 1.3 meters per second squared. It's pretty realistic for a car. Now think about race cars and acceleration. Everything here on this Formula One car is really there to create a very large mass, keep a very large force while keeping the mass as minimal as possible. Okay? Big tires, lots of grip on the road. Almost no room for the driver. Minimize that mass, it might slow it down. Most of the mass, because these are made out of different types of composite materials, either a fiberglass, which is a composite, or carbon composite, the main structure of it is fairly light. Really the engine gives you most of the mass of this vehicle right here. So race cars, lots of force from a very powerful engine, very little mass or a minimal amount of mass to prevent it from slowing it down. Sprinters achieve a tremendous amount of acceleration by having high strength. They're very muscular, yet they have very little, fat on them that would add to their mass. Same thing with most runners. They want to maximize the amount of force they can create, okay, and minimize the amount of mass that's going to drag down their inertia or increase their inertia. Again, units of force, newtons are the SI unit for force. In the imperial system, in the US customary system, pounds, ounces, and tons are typical units of force. We normally think of them as related to weight. Weight is actually a force. So weight is the force of gravity. Okay? But typically, if we're talking about other forces and we're using US customary units, we're probably going to talk about them in terms of pounds. How many pounds of force? The SI units of force, of course, were given to, the namesake comes from Newton. 1 Newton is equal to 1 kilogram meter per second squared. And a Newton's a slightly smaller unit than a pound. It's somewhere between 1/4 and 1/5 of a pound. Okay? So if you want to convert from Newtons to pounds, we have to multiply by 0.2248. If we want to go from pounds to Newtons, we divide by this number. Once again, mass and weight are two very different things. Mass is a measure of a quantity of matter. Okay? The more protons, neutrons, electrons, whatever something has, the more mass it has. And mass is measured in kilograms if you're using SI units. That is very different from things like weight. Weight, although it's related to mass, because weight is a force of gravity, and mass, of course, is how much matter something has. It's related by the acceleration of gravity. Okay? One is a force, one is a measure of inertia. Take, for instance, this Delta IV heavy rocket. This is one of the most powerful rockets that we have to put objects into orbit. It has 3 engines, each generating about 3 million newtons of force, okay, for a total of about 8.67 million newtons. And the weight of the rocket is 7.35 million newtons. So on liftoff, when it's first leaving the launch pad, we'll have 8.67 million newtons pushing upward. Gravity is going to have a force of 7.35 million newtons downward. All right? So when we use Newton's second law, we've got to be careful here. There are 2 forces acting on this. An up force and a down force. We take the difference between the two, and the total force acting on this rocket is 1.32 million newtons. Okay? So, F equals ma. We'll use the number of newtons total related to its mass. The mass of the rocket is 7.5 times 10 to the 5th kilograms. And to get the total acceleration, force divided by mass, total force, thrust minus weight, gives me an acceleration of 1.76 meters per second squared. Now it's important to note here, as the rocket goes higher and higher, its weight is going to become less and less. But the total thrust is going to be pretty much the same. Okay? They do ramp up and ramp down the engines. If anybody knows about this, they actually have to drop the thrust a little bit during part of the ascent, because what happens is they would have too much aerodynamic pressure in the lower atmosphere. What also happens is the center rocket actually throttles down a little bit, whereas the side rockets burn out first so that they can be ejected and they can reduce the amount of weight on the rocket in the end. Here's the Falcon 9 rocket. It has its own heavy configuration too, where they put 2 side Falcon 9s on the center booster. Here, each engine provides 850 kilonewtons of thrust. How many? Falcon 9, I think it has 9 engines. Maybe that's why they call it the Falcon 9. That's a revelation to me. So the total force here of thrust is 7,650 newtons on takeoff. Obviously, the weight is going to subtract off from that, But again, you can calculate the acceleration of any rocket by taking the thrust from the engines minus the weight of the total rocket and divide it by the mass. Now, when it takes off, all 9 engines are firing. Why? Because to achieve any appreciable acceleration, they need the force from all the engines, because the mass, all rockets, are pretty much filled. Or the tank, it's a liquid kerosene and liquid oxygen rocket. All the tanks are full of fuel and oxidizer. Okay? But as it goes higher and higher in its trajectory, the fuel is being burned off as well as the oxidizer. And when it's finally in orbit, it has very little, or when the first stage is spent, it has much less mass. So when it comes down and lands, you actually only have to light one rocket because it's a very, very small fraction of its original mass. Okay? So kind of cool if you ever watch these things. Falcon 9 is an extraordinary rocket in that it can take off and land and become reusable. I think the record for uses in a single rocket are 6 for these. So it's very much like the space shuttle was, in that it can be used in multiple missions. Another example, a little more down to earth. Here we have an airboat. The propeller from the fan gives us 770 newtons of force forward. You have a mass of 350 newtons. Kilograms. Notice we have scientific notation. You should know scientific notation. And if we take the mass and the force, we can calculate the acceleration. The acceleration is a force divided by the mass. This boat, when it first goes, can accelerate at about 2.2 meters per second squared. Now, forces are basically any push or pull on an object. A gravitational force would be attraction between any two objects due to their mass. We have gravitational forces, we have electric forces, we have magnetic forces. Later on, we'll look a little bit more about Newton's universal law of gravity. Okay? But for now, the force due to gravity, we'll say, on the surface of the Earth is 9.8 meters per second squared. Okay? Something has to be really, really massive to produce a gravitational field that we can feel. Again, weight is the force of gravity. We'll use a W here, which is its mass times acceleration of gravity, 9.8 meters per second squared. So again, if you want the weight of something, you can convert F equals ma to weight equals mass times acceleration. And for instance, take an 80 kilogram person once again. Now, the acceleration that we use is 9.8 meters per second squared, even though they're not accelerating. Einstein's theory of general relativity says it's almost like we are accelerating. But we get 80 times 9.8, that's 780 newtons of force, that's weight. And again, if you want to convert newtons of weight into pounds, we have to multiply by this 0.2248 pounds per newton conversion. So a 500 newton person would be extremely light. This would be like a jockey on a thoroughbred. 500 newtons is very, very small. Somebody who's closer to my weight, I hope I'm not up to 180 pounds. Maybe I am. But again, taking 180 pounds, if we want to convert that to newtons, 0.2248 pounds per newtons, I'd weigh about 800 newtons. So again, weight and mass, two different things. If you are 100 kilograms, say we have an astronaut who's, a total of 100 kilograms, including their spacesuit. On the Earth, they would weigh 980 newtons. On the Moon, where the gravitational force is less, where the acceleration of gravity is less, we would weigh much less, about 1/6 of what you would do on the Earth. Here, 162 newtons. In fact, on all these different planets, you would have a different weight because on each different planet, there's a different acceleration of gravity. Okay? On the Moon, you'd be very light. On Pluto, you'd be very light. Mercury and Mars, you'd weigh about a third of what you do on the Earth. Venus, you weigh about the same. Same is true for Uranus, Neptune, and Saturn. If the cloud tops were solid surfaces, you could stand on them, you would feel slightly heavier, about 10 to 20% heavier, but not much. Jupiter, however, you'd have a problem. If its cloud tops were, in fact, solid, you could barely stand up at 2.5 times acceleration of gravity. Let's talk about another force, friction. When two surfaces rub against one another or are in contact, okay, there is a normal force which doesn't allow the two objects to get any closer, okay? Like I'm pushing down on the floor with a normal force and the floor pushes up with me with a normal force. And there's a force of friction which is a transverse force. Because the surface of these two objects will interact, there will be some stickiness between the two surfaces. They will adhere to one another somewhat, and this will create frictional drag. Okay? Now, when a block is on a surface, typically the force of friction is less than the weight of the block. Okay? Let's say this block is 10 kilograms. Weighs 10 newtons. Let's use newtons instead. Let's say this block has 10 newtons of weight. The surface will push up with 10 newtons of weight. The normal force, that will be less than the frictional force. Okay? Now the frictional force, okay, if the two surfaces are sliding, or there's no force on them, then it can be all the way down to zero. But the frictional force is always less than or equal to what's called the coefficient of friction times the normal force, how hard the two surfaces are pushing together. The coefficient of friction is completely dependent on the materials. The two materials are very, very smooth and don't have a lot of interaction, like Teflon, they'll slide very easily. If the two surfaces are very sticky, like rubber and concrete, then we're going to have a high coefficient of friction. How much the molecules like to adhere to one another determines the coefficient of friction. Steel on steel. Inside an engine, you typically have the cylinder made out of steel and the engine block made out of steel. If the two came in contact with one another, the coefficient of friction would be very, very high because there has to be a tight fit, large normal force. We get about 74% of the normal force, and essentially the friction would cause the engine to heat up and seize. But because we add oil, okay, we lubricate this, the coefficient of friction is much less. The amount of energy we lose through friction is much less. The engine won't heat up and seize as a result. Copper on steel, usually the rings used to seal the cylinder are made out of copper. Rubber on concrete, you've got really good traction on concrete because the friction, which keeps your shoes from slipping, okay, has a high coefficient of friction and doesn't want to move transversely. Teflon is a great non-stick surface because Teflon, PTFE, polytetrafluoroethylene, is a very inert molecule. It doesn't really like to react with anything, and therefore has a very low coefficient of friction. The synovial joint fluid lubricates the joints in your arm, in your legs, and your knee very, very well to keep that coefficient of friction pretty close to zero. So again, friction is proportional to the normal force. The more the two surfaces are pushed together, the more friction there is trying to stop the two surfaces from sliding. The force of static friction, when the surfaces are locked together and aren't moving, is generally greater than if the forces cause the two surfaces to move. Again, coefficient of friction depends on the surfaces that are in contact, the materials that they're made out of, and the direction of friction always opposes motion. So if you try to go one way, friction pushes against the direction you're moving. Friction can be good, gives you traction, it prevents you from sliding. If you're on ice, your friction drops, and therefore you're much more likely to lose your balance. But on a dry surface, that friction keeps you from sliding with respect to the surface. And again, synthetic rubber is typically used on the bottom of shoes to have good traction, which is really friction with the ground. Same thing with rubber tires. Also have good adhesive forces with the ground, keeping you from slipping. In racing, they actually use soft rubber because of its very adhesive properties. The soft rubber will wear down very, very quickly, and you have to replace these tires, but it keeps the car in contact with the traffic so it doesn't slip off the road. And as we said, our joints are lubricated with synovial fluid, very, very low coefficient of friction. When our joints wear out, we get arthritis, and this arthritis causes the joint to swell, giving us quite a bit of pain. Back to these race cars, you'll see these aerodynamic surfaces on race cars. They're actually inverted airfoils, and they cause the car to push down. What they're doing is they're actually increasing the normal force. Even though this car may, perhaps weigh 10,000 newtons, you can get much more downward force, maybe 12,000 newtons, maybe 15,000 newtons, with the air being deflected upward, pushing the car downward. And again, tires actually do better when they're rolling with the road. Okay, we call this static, because each surface is moving with respect to one another. If the tires are slipping, then the coefficient of friction actually drops. You can lose 20% of your traction once the tire starts slipping. So many cars, well, almost all cars today, are equipped with not only anti-lock brakes that prevent the brakes from stopping the rotation, but also traction control, which keeps the car wheels spinning. You can do a little measurement of friction if you have a small scale. Drag some object across the surface, okay? The force it takes to drag it compared to the object's weight, okay, drag force divided by the weight will give you how much the coefficient of friction is. So for instance, this battery right here, if I measured its weight to be 58 newtons, and I measured the drag force to be 11 newtons, one divided by the other will give you the coefficient of friction, and here the coefficient of friction is 0.19. Viscosity is another type of friction. Viscosity, however, is not the friction between two surfaces, okay? It's rather the resistance of a fluid to flow. All fluids, except for superfluids like liquid helium, will have some internal resistance that will slow down their flow. The reason for this is an internal cohesion of the molecules. Molasses is very, very thick because molasses has a lot of sugar molecules in it, and sugar molecules like to stick together. Air resistance is another form of friction. As you fall, okay, you accelerate downward. We talked about how quickly you can accelerate as you free fall. But you never really keep accelerating forever. You actually begin to slow down in terms of your acceleration. This is graphing downward velocity as a function of time, until finally your velocity never gets any greater. We call this terminal velocity, meaning that you won't fall any faster. The problem is human beings reach a terminal velocity of about 55 meters per second, which is well over 100 miles per hour. So even though you will stop accelerating as you fall at some point, hitting the ground at over 100 miles per hour is guaranteed to be fatal. So what do? We increase air resistance with a parachute. And this will drop the terminal velocity to 2 or 3 meters per second, which is completely manageable.